Hello everyone, this is Dr. Tissa Munasinghe. Let's talk about the building blocks of the solid earth, minerals. There are about 4,000 minerals, but most rocks are made of only a handful of those, maybe 15 to 20 different minerals. What we are going to do is to talk about them. We'll learn how they form, why they form, and why do they look different. So let's go and talk a little bit about minerals. First, let's make a list of some uses of minerals. The first one that comes to our mind is halite, which is the salt. We call table salt, that is sodium chloride. It's one of the most common uses in everyday life. Then we have quartz, a mineral that is used to make glass for used around the houses and in computer screens, aircraft windows. Then gypsum is another mineral that the primary ingredient for drywalls. And then steel, which is made of iron combined with other metals. The iron comes from the mineral called hematite. The primary supply of iron is coming from hematite, and that ends up converted into steel at one point. Then bauxite is the mineral that you extract aluminum from. The diamond, everybody knows, is used as a jewelry and as a cutting medium. Then there's a mineral that's not very well known. It's called lepidolite. It contains lithium, and that's the ingredient in lithium-ion batteries, which is the battery that is powering all the electric vehicles and many other devices. Then we have gold. Besides as a jewelry item, gold is used for many situations where great conductors, electrical conductors. And then, for example, another one is called feldspar. Feldspar is the primary ingredient in ceramics. Ceramics also is a basic material that is used really commonly. So these are only some of the uses. There are quite a few more uses of minerals, and minerals are in our everyday life. But for us who are interested in the geology of the solid earth, the most important use of minerals is the minerals indicate what's going on inside the earth. For example, when you find diamond, which forms under extreme high pressures and temperatures, when you find diamonds on the ground, then you know the diamond forms at very high temperatures and pressures that is existing near the bottom of the mantle. Now these diamonds are sitting on the ground at the surface of the earth. So that tells us that there's something that brings up the rocks from underneath the mantle all the way to the surface. So this is a very simple example of how minerals help us understand what's going on inside the earth. So we look at various minerals and tell ourselves the history behind all these rocks. Now let's see where minerals stand in the whole scheme of the solid earth. The solid earth, we draw an arrow and say that arrow represents the phrase made of. So solid earth is made of rocks, and rocks are made of minerals. Minerals are made of molecules, which is a combination of atoms. So molecules are made of atoms. Atoms are made of subatomic particles, neutrons, protons, and electrons. So we call these subatomic particles. And neutrons, protons, and electrons are made of quarks and muons and gluons and all that. We don't go there, but we stop at the tiniest level for our discussion: neutrons, protons, and electrons. First, let's write down some definitions. What is a rock? A rock is a solid made of one or more minerals. Then we define what minerals are. A mineral is a natural, inorganic, crystalline solid. So minerals has to be all four of these. Just to talk about what's going on about inorganic. Inorganic means no carbon hydrogen bond. Organic means carbon-hydrogen bond. So we will talk about these bonds a few minutes later, but all living things have carbon bonded to hydrogen atoms. So we call that carbon-hydrogen bond, and we call those molecules organic molecules. So minerals cannot be organic, it has to be inorganic. Then, what is a molecule? A molecule is a combination of atoms. Then what is an atom? An atom is the smallest unit of a chemical element. What does that mean? Let's see. You take a piece of gold and you cut into two. What do you have? You have two pieces of gold. You keep cutting it, you have tiny pieces of gold. So at one point, this is not practical, but if you can cut to the finest level, then at one point, the smallest piece will become a gold atom. If you can cut it, then it will not be gold. It will be neutrons, protons, and electrons. So an atom is the smallest unit of a chemical element. So what are atoms made of? They are made of subatomic particles. So now let's talk about subatomic particles. There are three subatomic particles: neutron, proton, and electrons. The symbol for neutron is uppercase N. Symbol for proton is uppercase P, and the symbol for electron is lowercase e. Okay, it's not uppercase. So let's define these particles. To do that, we'll draw a small table that shows the name of the particle and the mass of the particle and then the charge of the particle. We start with protons. Protons have one mass. It's called atomic mass unit, or AMU. And protons, every proton has a unit electrical charge of plus. So they have a positive charge. Electrons have no mass. Actually, the mass is so small, it is considered zero mass. And it has a single negative charge. Then we have neutrons that has one atomic mass unit and a zero charge. I'm sure you can see the interesting thing in here. If you draw a line right here and then add these two, the first two, what do you get when you add plus to a minus? You get a 0. What do you get when you add 1 to 0? You get 1. So that means if you add a proton and an electron, you get a neutron. So we write a neutron equals proton plus electron. This would be a good time to just say that when stars explode, when they die, electrons and protons fly out so fast away from the star. They run into each other. When a proton hits an electron, they just combine and they become a neutron. And of course, neutrons break into protons and electrons in the same process. So this is the relationship between neutron, proton, and electron, which are the subatomic particles. So how do atoms form? Simple. If you can bring protons, electrons, and neutrons together, you can build an atom. So we write atoms form by combination of protons, electrons, and neutrons. Where do they happen? They happen inside stars. So new atoms form inside the stars. Stars emit light and other forms of energy by burning. It's actually a simple word for the actual reaction, which is called nuclear fusion of small atoms like hydrogen. So right now inside our sun, which is a star, hydrogen atoms fuse, combine to make an helium atom. So these two hydrogen atoms make a helium atom. And then when it runs out of hydrogen, it will start fusing helium to make lithium, and it keeps going on until it reaches iron. After that, it cannot fuse anymore, then the star dies. So what is happening right now in our sun is burning hydrogen, or nuclear fusion of hydrogen.
The star has run out of hydrogen fuel. The nuclear fires that have kept it burning for millions of years have gone out. As it cools, it shrinks. It starts to collapse under its own weight. It crashes inwards and explodes.
So when the star runs out of fuel to burn, it stops generating heat, it shrinks, collapses, and that causes buildup of secondary type of heat which explodes the star, and we call that a supernova you saw in the last little video. So in the supernova, you can see all these gases and dust actually flying out of the dying star. So what is actually flying out? Besides many elements, what's flying out actually is electrons, protons and neutrons. And not everything goes in the opposite direction. Some cross paths and they run into each other at near speed of light. When the electrons, protons run into each other, they build brand new atoms. Let's write that down. The second place where brand new atoms form is during the death of stars. These events are called supernova. You saw it in the last little video. What happens to a star that runs out of fuel? Then the whole star explodes and causes a planetary nebula. In the planetary nebula, electrons, protons and neutrons, they clash, and that collision makes an atom. So that's another brand new way of making atoms. This method is called nucleosynthesis. So atoms form by nuclear fusion and by nucleosynthesis. Two different times, two different forms. So what does the inside of an atom looks like? Let's draw the structure of an atom. Here is the center of the atom, and it contains neutrons and protons in a little bundle called the nucleus. Around the nucleus, electrons are spinning at the speed of light. They spin so fast you cannot see the individual electron. All you see is a cloud. So it looks like a solid. It's not actually a solid, it's just an electron being everywhere at the same moment. Although we draw it like this, this is not the actual scene. If the nucleus is the size of a pinhead, the nearest electron will be about half a mile away. So that's a huge gap compared to the size of these particles. That's why we say most of the atom is actually empty. But the electrons are spinning so fast, it looks like as if there's a solid in there. So in this path, you can have another electron spinning at the same time. Then, if there are any more electrons than 2, it will go into another path we call orbit, and the electrons will spin in that orbit. So that is what the simple atomic structure is. So we have electrons in different orbits spinning at the speed of light. These orbits are called energy levels, or simply known as shells. So here's an animation that shows what's going on inside an atom. This is slowed down quite a bit. The electrons spin so fast, it looks like a cloud when you look into an electron, because the electron is everywhere. This is the slow motion. So this is another animation that shows what the electrons do inside an atom. They are going around different shells or different orbits around the central nucleus where the neutrons and protons are. So this is still slow. If you think about speed of light, which is 186,000 miles per second, you don't see an electron at any point anywhere. It looks like a cloud. Here's another animation that shows what the electrons do. So the center is neutrons and protons shown in the middle, and around that electrons are spinning really fast. So that is the simple explanation of what atoms look like inside. So when you draw an atom to explain how atoms behave under different conditions, we draw the nucleus at the center and some circles around it. This drawing is commonly known as the Bohr atomic model. The actual atom doesn't look like a bunch of circles, but basically it represents the concept. So in the middle we show the nucleus, and around that we show the first shell. And then first shell can contain only 2 electrons. The second shell, if there are more electrons, it will go to the next energy level or next shell, and it can hold 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. That's all it can hold. If there are more electrons, it will go to another shell. So this is called the Bohr atomic model, and this is called the outer shell or outermost shell. So each atom has a shell that is considered the outermost shell, and that shell has to be filled to capacity for the atom to become so-called stable. We'll talk about that. Here is an animation that represents the aluminum atom. Symbol for aluminum is Al, and it has 13 protons, and this atom has 14 neutrons. Another animation that represents conceptually what atoms look like inside, if you can see them. But in real life, electrons are not going in circles. They are going in orbits of different shapes. So this is more like an atom. You see the pink part here and here. They are looking like clouds. We call them orbits. It looks like a cloud because the electron is everywhere at every moment. So it looks like it's a solid object. It is not a solid. Most of the atom is empty inside. And then we have, here's orbit 1 and here's another orbit. If you take a chemistry class, you'll be discussing these various types of orbits and how they change from atom to atom. We are not going to do that. Just get an idea what atoms look like inside. Okay, but we'll use the simple Bohr model to explain and describe atoms. As we said before, when atoms build up because electrons, protons and neutrons bombard it at super high speeds. As it builds up, it has to follow a certain rule. Each shell can have only so many electrons. So the way these orbits or shells are filled is like this. First orbit, 2 electrons. Second orbit can have 8, then third orbit like that, fourth orbit, fifth orbit, and the sixth one can have 32 and so forth. Okay, so if after the first orbit, the third electron will go to the next orbit or next shell. So that's the concept of filling pattern of the electrons in a building atom. Let's write down some notes on various forms of atoms or various variations of atom. In a simple normal atom, the number of protons equals number of neutrons equals number of electrons. If the number of neutrons and protons are not equal, then it's called an isotope. In case you were wondering, that symbol means not equal. Then if the number of number of protons is not equal to electrons, then you have an ion. Each atom is labeled by its atomic number, which is the number of protons. So the atomic number of any atom is the number of protons that atom has. And the mass of an atom, or which changes with the number of neutrons and protons. So we have a quantity called atomic mass, is the average total mass of an atom, which is made of the number of neutrons and protons. But some atoms have isotopes of the original or normal atom, so there is a slight variation. We'll write that atomic mass depends on the number of isotopes that is found in nature for that atom. For our class, we'll ignore for now the isotope part. So for our class, atomic mass is simply the mass of the neutrons and protons. So we get that by adding the number of neutrons to number of protons. Let's take a brief look at all the atoms that are found in nature. It is shown in a very famous chart called the periodic table. In here, all the chemical elements that are discovered are listed. The simplest atom is hydrogen with one atomic number. Atomic number of hydrogen is 1 because it has 1 electron, 1 proton, 1 neutron. And then you go to oxygen, it has 8 electrons, 8 protons and 8 neutrons. If you look at sodium, sodium has 11 electrons, 11 protons and 11 neutrons. If you think of chlorine, chlorine has 17 electrons, 17 protons and 17 neutrons. It goes on like that. If you think of gold, it has 79 of each. The biggest one has 118 electrons, 118 protons and 118 electrons. So that's the periodic table of elements. This shows the properties of various chemical elements. You don't have to memorize, you don't have to be able to read this, but just introducing to the concept of the periodic table, this is a great chart that tells us how various chemical elements behave. We need to know, not us, but geologists, we need to know how these elements interact with each other, forming minerals inside the earth and outside the earth, so that we understand what's going on in and on the earth. So what do we have? What kind of elements do we have in and on the earth? If you look at the whole earth, inside and outside, this is what we have. So most of the earth is made of iron. Then oxygen. Then silicon. So 15, 30, 45, 45 plus 35 is 80. 80% of the earth is made of iron, silicon and oxygen. And the rest, you see, the next most common one is magnesium, and then it goes on. But if you look at the earth's surface or the crust or the upper part of the earth, here is the composition. Most of the crust that we walk around, upper part of the lithosphere, is made of oxygen. And the second most common one is silicon. So most of the earth's surface or surface rocks are actually oxygen and silicon. These are called silicates. We'll write that another time, but also, so this is silicate. So most of the crust is made of silicates, silica and oxygen. And then aluminum, then iron. We don't have a whole lot of iron near the surface or in the crust, but there's lots of iron in the earth. Most of the earth is iron, but most of the iron is, of course, inside the earth. We learnt about that. Inner core and outer core is made of totally 99% of iron. Okay, so these are some numbers. You don't have to memorize it, but just good to know what different parts of the earth is, what kind of chemical elements different parts of the earth is made of. All this time we were talking about the chemical side of atoms. Now let's talk about the geological side of it. So how do minerals form? Okay, let's go back a little bit. Let's remind ourselves that an atom to be stable, they have to have their outer shell filled. If they are not filled to capacity because they have extra electrons or missing electrons, then they are called unstable atoms. Remember, systems and stability. All unstable systems try to become stable by changing. This change that's going on between and among atoms is called reactions. So unstable atoms react with other unstable atoms and make something called molecules, combination of atoms. And the sum of the molecules make crystals. Not all molecules make crystals. For example, a DNA molecule is not a crystal in our body, but sodium chloride molecule in nature forms a crystal. You'll see it later. And these crystals are what we call minerals. So summarize all these, we say how do minerals form? We say minerals form by combination of unstable atoms. So here is a stable atom. In the inside shell you have 1, 2 electrons. In the outer shell you have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So both shells are filled to capacity. Therefore this atom is a stable atom. Here is an example of two unstable atoms. So we have sodium, which has 11 electrons. You can see from this number, this represents the atomic number. Sodium has 11 electrons, 11 protons and 11 neutrons. So it looks like this. If you count, well, quickly count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. Notice that the outer shell has only 1 electron. So this is the outer shell. It has only 1 electron. It's very unstable. Sodium is so unstable, if you put a piece of sodium, which is a metal, into water, it will explode. That's how unstable it is. So that is an 1 extra electron. Then we have chlorine, which has 17 of each. That atomic number is 17, so that means 17 electrons, 17 protons, 17 neutrons, and it looks like this. If you count, you will find it's all 17. Right here, it has, on outside it has 7 electrons. 1, 2, 3, 4, 5, 6, 7. It needs 8. So 1 is missing. So we have sodium 1 extra electron, chlorine 1 missing electron. What do you think will happen when you put these things together? You guessed right. Electron from the sodium goes to chlorine and then settles down in the outer shell. Now both of them are stable. So as we said, this is the same diagram as the previous one. So what happens now is this electron will go to right there, and we call that electron transfer. We can call it electron jump or donation, receiving, anything. Just electrons go from one atom to another. That is what happens. Now we have a new situation. Notice that there's nothing going on here, so this is not existing. This becomes the outer shell, and it is filled capacity because it has 8 electrons. And in here, in chlorine, that is the outer shell, so it is filled to 8 maximum capacity. So both are stable now, except there's a little minor detail that we have to think about. Right here, 1 electron left, but the proton did not go, so there's 1 extra proton there. And here you have what we call a positive ion. Remember, when the number of protons is not equal to number of electrons, you have an ion. Because protons are positively charged, this ion is a positive ion. This is an extra electron, and there's no proton to cancel it, so we have 1 extra negative charge, so this is a negative ion. So when you have a positive and negatively charged particles, what happens? They get attracted to each other, and that attraction is very strong, and that causes the negative ion to get stuck to the positive ion, and this being attached, attracted, stuck is called a bond. So the electron transfer caused the formation of a bond. Because this bond was formed due to 2 ions attracting or attaching to each other, we call this an ionic bond. So the sodium atom became a positive ion, so now we call that the sodium ion. And the symbol for sodium ion is this. Na is the symbol for sodium. You can check the periodic table. Na positive of Na plus means sodium ion. And then we have the negatively charged chlorine. Now we call that the chloride ion. And these positive and negative charges are attracted to each other, and therefore they are attached with a bond that we call ionic bond. Let's look at what happened. Sodium is a very reactive, explosive metal, very dangerous, combined with extremely poisonous gas called chlorine, and built a molecule that is called sodium chloride. The symbol for sodium chloride is simply their symbols put together. The sodium and chlorine got together and built a molecule called sodium chloride. I'm sure you have heard of this. This is our table salt, halite. Mineralogically, it's called halite. Guess what happened? 2 extremely dangerous and poisonous atoms combined to make one of the friendliest molecules to all humans. We all love salt because we need salt to communicate inside our bodies. That's why we love salt. So we have halite. So salt crystals or halite crystals look like this. We'll talk a little bit more about that later. And now you know how this formed. So we'll write what an ionic bond is. Ionic bond is an attachment between oppositely charged atoms. And these charged atoms are called ions. So ionic bonds are attachment between ions or oppositely charged atoms. Here's another way the atoms combine. Here is a silicon atom that has an atomic number of 14, meaning there are 14 electrons, 14 protons and 14 neutrons. In the outer shell we have 1, 2, 3, 4. To be stable, this has to have 8, but we have only 4. So for unstable atoms quickly try to become stable by doing something about it. So this atom has to have 4 electrons, or it has to give 4 electrons away. What does it do? Well, fortunately, if it comes to contact with oxygen that has 8 of everything, as you can see from the atomic number, 8 of protons and 8 neutrons, 8 electrons. So outside it has 1, 2, 3, 4, 5, 6 electrons. Not enough. You need 8. What do? You share with silicon atom. But that satisfies oxygen, but silicon atom needs 2 more electrons. So what does it do? It does the same thing with another oxygen. So what do we have? We have electron sharing. Now if you look at all the outer shells of oxygen and silicon, they all have 8. They don't give an electron or they don't get an electron, they share electrons. That sharing creates a bond called covalent bonds. So we have a silicon atom attached to 2 oxygen atoms, and these attachments are called bonds, special type of bonds, covalent bonds. So what do we have? We have a molecule we call SiO2 or silicon dioxide, and this is quartz, also known as silica, which makes glass. So here's some quartz, examples of quartz mineral, and they form by sharing electrons, and we call that bonds, covalent bonds. So we write covalent bonds are attachment between atoms by sharing electrons. Now let's look at an animation that explains how the ionic and covalent bonds form. The narrator in there refers to something called valence electrons. What he is referring to is the number of electrons in the outer shell of all the atoms. Instead of silicon dioxide, the narrator explains how water molecule, which is H2O, forms. Let's watch.
Ionic bonding occurs between 2 atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with one valence electron needs one additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still one short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
Geologists have discovered about 4,000 different minerals on the earth. So we have to separate them into different categories, which is called classification. Let's talk about classification of minerals. Minerals are classified into 2 classes. Silicates that contain silicon and oxygen atoms, and then non-silicates, meaning they don't have silicon and oxygen bond or silicon and oxygen atoms. First, let's talk about the silicate minerals, or commonly known as silicates. They are classified into 2 groups. First one is called ferromagnesians. Ferro refers to iron, magnesium of course refer to magnesium. So they have iron, Fe is a symbol for iron, ferro is a reference, and magnesium, Mg. Some examples of ferromagnesians are olivine, pyroxene, amphibole, and biotite. You might wonder if you are going to remember all 4,000 minerals. No, you are going to remember about 15 because that's the most common set of minerals that are found on the earth. Getting back to ferromagnesians, they are generally dark in color. When we say dark, you are referring to black, dark gray, and even green is considered dark. And they are high density because they have iron and magnesium in them. Iron and magnesium, or in other words, ferromagnesians, are the minerals that form the primary component of rocks that forms the seafloor. So we say ferromagnesians are the main component of oceanic lithosphere. Ferromagnesian composition is called mafic composition. So this is something that you probably heard before in the structure of the earth. Mafic refers to magnesium and iron, which is Fe. So that's why I say Fe. So mafic refers to ferromagnesians. Let us look at some examples of the ferromagnesians, the most common ferromagnesians, starting with olivine. Here's what olivine, this green mineral found here, right here, this green mineral, that is olivine. This is some other form of ferromagnesian, dark in color. Okay. Then we have another example of olivine. It's a beautiful tiny crystal of olivine. And here's another examples of olivine. Some beaches like in Hawaii is very rich in olivine sand. So those beach sands look like this, primarily green. Now you can imagine why it is called olivine, because the color comes from the olive green from the olive. Olivine is considered a semi-precious stone, so they can cut and polish olivine to make gemstones. Now let's look at some pyroxenes. So here's an example, some examples for pyroxenes. That is the most common pyroxene that you find in the surface rocks. This is a mineral called augite. You should be able to see the faint green color in here. This is actually super dark green. Here's another example for a pyroxene, and another and another. So you can see that they are dark in color, classic example for pyroxenes. Here are some examples for amphiboles. Notice the dark color that is common to ferromagnesians. And another common ferromagnesian near the surface of the earth is biotite. And this is what biotite looks like. Biotite make thin sheets. You can see the thin sheets. That's very typical of biotite. That is very typical of all kinds of mica. There are two kinds of mica that we will be talking about and remembering. The first one is biotite, the other one is muscovite. Muscovite belongs to the non-ferromagnesian group. Okay, so so we have mica in both groups, ferromagnesian and non-ferromagnesian. Now let's talk a little bit about the non-ferromagnesians. It's basically the opposite of ferromagnesians. So in here, these are silicates but no iron or magnesium. An example, some of the examples would be quartz, plagioclase, orthoclase, and muscovite. Non-ferromagnesian commonly are light in color. When we say light, white colored, light gray, and pink are considered light colored minerals. These are less dense than ferromagnesians because these don't have iron and magnesium in them. Remember, ferromagnesians make the main component of oceanic rocks, and the main component of continental rocks or continental lithosphere is non-ferromagnesians. So these are like ferromagnesians are called mafic, non-ferromagnesians are called felsic. The Fel comes from feldspar. And Si comes from silica. So it's rich in silica or silicon and feldspar. Now let's look at some typical non-ferromagnesian silicates. The most famous one is quartz. Here's some quartz. This is what you find clean quartz look like. Quartz is very common. Most of the beach sand that you walk on actually is made of quartz. Most of the sand on rivers, beaches, at home, in the backyard, most of them are quartz. So this is what some quartz grains found on the ground looks like. But some quartz are crystalline. So this is a geode, little cavity filled with tiny quartz crystals. And here's another type of quartz called rose quartz. The only difference is the color. This looks rose, and this one just looks white. And these are white as well. There are many different types of quartz. I'll show you in a minute. And here is the crystalline quartz. So you can see that these are crystals. Actually, all these are crystals too. These are very tiny crystals in here, but these are also pieces of crystals. And that's the perfect crystal. And you can see 1, 2, 3 crystals, plus some more. Here are some examples of plagioclase. The first look, it might look, all these look the same, but as you keep seeing them over and over again, you will see they look different. Plagioclase is a member of the family called feldspar. Plagioclase feldspar has calcium and sodium, various combinations of calcium and sodium. Then we call them plagioclase. If the feldspar contains potassium instead of sodium and calcium, then it's called an autoclase. Autoclays look like most of the properties of all these feldspars are the same. This one has a little difference in color. They are a little bit more pink than the other feldspars. So this, just to remind ourselves, this is also a feldspar. But this feldspar is made of potassium silicate. The previous feldspars are made of sodium and calcium silicates. Here is another common non-ferromagnesian silicate, muscovite. Muscovite is the other member of the mica family. So muscovite mica belongs to the non-ferromagnesians. Biotite mica belongs to the ferromagnesian family. So here is what muscovite looks like. They also form thin sheets. All micas make thin sheets. So we just finished talking about the common silicates. Now let's talk about the non-silicate minerals. Obviously, they don't have silicon and oxygen bonds. They have oxygen but no silica. They are classified into several groups. Carbonates. The most famous example for carbonate class is calcite. Halides, halite, the rock salt or table salt. Sulfides, example would be pyrite. Sulfates, example would be gypsum. Oxides, an example would be hematite, which is iron oxide. Hydroxide, an example would be iron hydroxide, limonite or limonite. Then phosphates, an example would be apatite. And native elements, an example would be gold. So there are other native elements like silver, copper, platinum. All these things can be found by itself. They are not combined to anything else. In the next few slides, we'll be looking at some of the images of these non-silicates, starting with calcite, which is a carbonate. See, remember, the same mineral can look very different because their crystal form is different. Next we have halite, which is a halide, common salt. Here's a tiny grain of halite. If you look at your table salt under a microscope, this is what you will see. Beautiful, clear, cubic crystals. Here are some other examples of halite. Notice that they are making cubes. This halite looks pink because there's a bacteria growing inside it. Let's look at a member of the sulfide family, pyrite. This is also known as fool's gold because it looks like gold. Notice the perfect cube that pyrite makes. When you have a whole bunch of cubes to put together, this is what it looks like. It really looks like gold. Gold doesn't have cubes. So when you see cubes, you can say, it's not gold. So these are other hand samples or examples of pyrite. Then we look at gypsum, which is a sulfate. Notice the different ways gypsum is found. It is a very soft mineral. You can scratch gypsum with your fingernail. Now let's look at an example for an oxide, in this case hematite. Hemo refers to blood, red colored. It doesn't look like red, but actually This looks like a metal, but when you draw, if you look at the powder, it looks very red. So here are some examples of hematite. Some people break hematite into small pieces and polish them, and they look like this. And some even magnetize them, so they are nice tiny little magnets. And some make necklaces and all kinds of other jewelry out of this shiny or shined hematite crystals. Last one was iron oxide. Let's look at iron hydroxide, which is the hydroxide family. This is called limonite or limonite. They look like this. They have a little brownish, yellowish color. Now let's look at some examples for the phosphate family. An example would be apatite. This is what apatite. Those are two apatite crystals. It's a beautiful apatite crystal. And here are two apatite crystals of different color. Remember, one mineral can have different colors. All because of the impurities, chemical atomic impurities inside the crystal gives a different color. Finally, let's look at some native elements. Native elements means the atom is by itself. It is not bonded to any other atom. The most famous example, of course, is gold. So this is how the gold is found in this quartz, inside the quartz. So you can see the light colored area right here is quartz, and that of course is the gold. Gold forms inside quartz. When we talk about igneous rocks, I'll let you know how this forms. And then they eventually get broken and then get washed to streams, and that's how many people find gold in streams, but they form inside magma. Another example would be silver. Same story. It's also found inside quartz. The white part is quartz, and you can see how the silver crystals look like leaves. That's the crystal form for silver. Then we have copper. Even copper is found. Copper is very reactive, but sometimes it's found by itself because it didn't have any other atoms nearby to react with. So it is found by itself. So this copper, metallic copper. Now what we are going to do is to make a list of various properties of minerals. The first property is called luster. Luster is referring to what does this mineral sample look like, the appearance of the mineral. The first luster we are going to talk about is called the metallic luster. These minerals look like metals. For example, here you are looking at pyrite. This iron sulfide. It looks like metal. It looks like brass, almost like gold. Gold doesn't look like that. They don't have sharp edges, but that's pyrite. Looks like a metal. And here's another metallic luster, galena, lead sulfide. It looks like steel, stainless steel. And then here's another sample that looks like metal, so a metallic luster. This is hematite or hematite. The next luster we are going to talk about is called vitreous, generally called the glassy luster. This is fluorite. It looks like glass. And this is a beryl. It's referring to this crystal right here. Okay, so the white part, ignore. This part is the crystal or the mineral with the vitreous luster. And the classic example for vitreous luster in this case, this is gypsum. It looks like glass too. So all of these have the vitreous luster. The next luster we are talking about is called the earthy luster. Earthy means it looks like dirt, no special features, just look like a rock sitting on the ground. Next we have the resinous luster, meaning the mineral looks like wax. And then we have minerals with pearly luster. Looks like pearl, not exactly like pearl, but this is the best explanation the luster pearly refers to. Looks like pearl. The next property of minerals is called the color of the mineral. So color refers to the color of the mineral. There's another luster coming up. There's another property coming up which is referring to the color of the powder. It is called the streak. When you say the color of the mineral, it's called the property called color. So here are some minerals that have very different colors. These are actual photographs of these minerals. You can see some of them can be really beautiful, but they are rare. And if you look at this, it's a tourmaline. It has very different colors in the single crystal. We will talk about this again, but I would like to let you know what makes the minerals have different colors. Primarily, what kind of chemical elements or atoms are in there, and secondarily, the way they are bonded. We'll talk about that later. Different minerals have different colors, but can you imagine one mineral having so many different colors because they are made of different arrangements and different kinds of impurities, chemical impurities in that. So we write one mineral can have many colors. For example, look at this. All these are quartz, silicon dioxide. Silicon dioxide, SiO2. So why do they look so different? Again, into the silicon dioxide sometimes getting little atoms, titanium atoms, iron atoms, copper and all kinds of other atoms get in there, and then that causes the color to change. If you are interested, we can talk a little bit about what actual physical side or physics side of color is. Basically, white color or the sunlight has 7 colors, and the 7 colors, you see them in the rainbow. The 7 colors get split by water droplets. That's how the rainbow is formed. So same thing happens when the light enters the crystal, and then the various wavelengths that gives color are absorbed. Whatever that is not absorbed, or whatever the wavelength that is not absorbed, comes out and gives that color to that substance, in this case the mineral. So these are all silicon dioxide, but they form differently and they have different impurities, so they have different colors and different appearances. The third property of minerals we are going to talk about is called the streak. Streak is the color of the mineral powder. Speaking of powder, how do you find the powder of a mineral? Simple. Imagine you are drawing on a piece of paper using a lead pencil. As you push the pencil against the paper and move it, it leaves a mark, simply a line. And that line represents a little bit of the scraped off lead left on the paper. And what's sitting on the paper is the powder of the tip of the pencil or lead. So when you draw a line, you leave a little bit of powder. That's how we test the streak of minerals. So here's an example. You can see this mineral, hematite, has a color like that. So mineral color and the streak is different. And here you can see it's different colors. You do that by drawing a line on a little piece of plate called a streak plate, which is actually a ceramic plate. So if you have a ceramic plate that is not shining, then you can do this, find the streak. Here's another example. All the lines show the color of the mineral powder. In other words, the lines are called the streak of that mineral. Here's another example. The next property of minerals we are going to talk about is called hardness. Hardness is how resistant a mineral is to scratching. So we write hardness equals resistant to scratching. Some minerals can be scratched with your fingernail, others you can't even begin to think. They are so hard, they will be scratching everything else. So for example, the softest mineral is called talc. That's why it is used to make talcum powder, the soft material. This has in the hardness scale of 1. The hardest mineral is diamond. Diamond is so hard to scratch. To scratch a diamond, you need another diamond. And diamond will scratch every other mineral. It has a scale of hardness, scale of 10. So the scale of the hardness was invented by a geologist by the name Moore. So the order of hardness is listed in something called Mohs scale. Let's take a look at it. Here is a Mohs scale. Goes from 1 to 10. The softest is talc and the hardest is diamond. So we have the numbers. So these are some examples of these minerals. Talc look like this, and gypsum sometimes looks like this, calcite and so forth. Okay. So remember, not all talc will look the same, not all quartz will look the same, not all gypsum will look the same. Nature is never perfect. Okay, so the second hardest one is called gypsum, and third is calcite. Your fingernail has a hardness of about 2.5. So your fingernail can scratch gypsum, yes, but it cannot scratch calcite. Fluorite has a hardness of 4. Copper has a hardness of 3.5. Sorry, copper coin. So you can scratch calcite with copper coin, and fluorite can scratch a copper coin. So you use these fingernails, knives, glass, steel, and all these commonly available substances to check the hardness of minerals, because that's one way we can identify a mineral. So the fifth hardest mineral in this list is called apatite, not apatite, apatite. Then you have feldspar family minerals. Then you have quartz. Quartz has a hardness of 7. So steel can scratch feldspar. Steel cannot scratch quartz. Quartz cannot scratch topaz because topaz is harder. And the second hardest mineral is corundum. This is also known as ruby. When corundum is found in gem quality, that means transparent and colorful, then it is called a gem. So ruby and diamond, ruby means corundum, and diamond are the hardest two minerals. So nothing can scratch. So they will always stay shiny. So they are used as gemstones. Everything else, if they are beautiful colored and see-through, transparent, clear, then they can be called gemstones, but not because they scratch over time, they dull out, the shininess goes away, therefore they are called semi-precious stones. So fluorite, apatite, feldspar, quartz, topaz, they make semi-precious stones. But I would like you to get the concept of hardness as listed in this. So somebody can ask you, is quartz harder than apatite or softer than apatite? No, then you can look at this table and tell yourself quartz is harder than apatite. If you take a hammer and hit a mineral, the mineral will break. The way the mineral breaks depends on the type of mineral, because different minerals have weak surfaces inside them. So when they are hit or stressed, they break along these surfaces called cleavages. So we write cleavages are weak surfaces in a mineral crystal. So the mineral breaks easily along this surface. Each surface or each direction is considered one cleavage. So some minerals don't have cleavage, so they have a zero cleavage, and some minerals break along 4 different surfaces, 4 different directions. They have 4 cleavages. So minerals cleavages can vary from 0 to 4. Let's look at some examples. Take quartz. Quartz, when they are broken, they don't break along a preferred surface. The surfaces of a broken quartz is always random because there's no specific direction. So we say quartz crystals or quartz mineral, this one, crystal quartz is different. This is milky quartz, rose quartz, smoky quartz. They don't have a preferred direction. So we say it has a cleavage direction of 0. But if you take muscovite, for example, a member of the mica family that contains biotite, muscovite and phlogopite, they break, look at this, they break along a single surface. So if you look at the lines in the minerals, they break along these lines. So when you can peel the surfaces off, so we say muscovite has one cleavage. If you look at autoclase, it breaks along 2 different surfaces, one here and one there. So the cleavages can be shown as one there, one here. So autoclase has 2 cleavage directions. And if you look at galena, galena breaks along 3 surfaces, one there, one here and one there. The 3 surfaces have 3 different directions, one like that, one like this and one like that. So we say galena has 3 cleavages. Remember, it's not the number of surfaces, it's the number of directions. And then finally we have fluorite. Fluorite, it will break along 4 different surfaces of different directions. 1, 2, 3, 4. This is fluorite with 4 cleavages. So by looking at a mineral, you can recognize these cleavages by noticing flat, shiny surfaces. So these are, the cleavage surfaces are flat and shiny. Okay, so that's the property called cleavages. Another property of minerals is called the form of the mineral. That refers to the way the crystal looks like, the external shape of individual crystal. Here are some examples. These minerals, they look like cubes, so cubic form, and they look like prisms, so prismatic. They don't have any form, they look like a pile of this crystal, the mineral. So we call amorphous, powdery. Then we have this very interesting form. It is called botryoidal. Botryoidal, they look like little blobs, like bacteria growing on a rock. That's malachite, and that's the way that crystal is found in nature. And then we have a plate-like crystals, kyanite, is called bladed form. And this is another form. This is asbestos. Look at this little fiber here. Look at all these fibers. These fibers, each fiber is a crystal. So asbestos is found as fibers, So we call this form the fibrous form. You see, minerals have very different properties. Geologists have found very unique different forms. So here are some examples of these forms. So if you look at these, minerals can be found in any different form. So in like this. So here, look at this. You saw copper like that, and a fluorite like this, halite and galena like that, quartz like this, fluorite like this, asbestos like this. So there are many different ways a mineral can look like. Another property of mineral is called density. Of course, we talked about density briefly in our basic concepts. Density is how densely the atoms are packed in a substance or in a mass. So closer the atoms are packed, denser the mineral is going to be. So one of the least dense minerals is halite at 2.16 grams per cubic centimeters. So Cc stands for cubic centimeters. Grams per cubic centimeter. That's one of the lightest or lowest density minerals. Then we think of gold. Gold is very dense, but that's not the densest mineral. The densest mineral is osmium, the metal. It's 22.59 grams per cubic centimeter. So when you get a chance, look at the densities of all these elements: silica, oxygen, carbon, nitrogen, gold. Then you realize osmium has the highest density as 22.59 grams per cubic centimeter. If you have lifted any mercury, you will notice that it's very dense, but this is the densest. It's very interesting to notice the density of different natural minerals. So why do minerals have all these different properties? Color, luster, form, density, crystal habit, all these different, because due to two reasons. The first reason is the composition, or what kind of atoms went into building the mineral. So the first factor that decides the property of a mineral is the chemical composition. Different chemical elements have different properties. The classic example is looking at the flames of various different materials. If you hold some fluid or some dust that has barium in it, the flame will look green. If the material has some strontium in it, it will be looking red. If it has lithium, it will look dark orange. If it has sodium, it will have this yellow color. Now if you see some of the parking lots, all the parking lots have these yellow colored lights burning all night long. That actually are called sodium lamps instead of regular inert gases inside. It has sodium vaporizing to give sodium ions running around inside the bulb, and it gives a yellow color. If you put some powder or liquid that has copper in it, the flame will be blue-green like this. If the material has potassium, it will be purple in color. So different chemical elements have different colors. So when you have these elements in a mineral, the mineral gets this color. I would like you to do a simple experiment very safely. When you look at the stove flame is generally blue. If the stove is working properly, it will be blue. Sprinkle some tiny drops of water to the flame. The flame will take orange shape. Why is it turning orange when the water hits it? Because our water has calcium in it. The color of calcium is orange or yellowish orange or orangish yellow. Look at that. So chemists use this test to find out what chemical elements are found in a liquid or in a little bit of dust. So the first factor that decides the properties of minerals is the chemical composition. The next factor that decides the property of a mineral is its structure. Structure refers to the arrangement of the atoms in a crystal. Let's look at some examples. Here are the arrangements of two minerals, halite and olivine. Remember halite, the table salt, and olivine, the olive green mineral. So if you look at the halite crystal, you can see that's chloride ion, negatively charged. That's a sodium ion, positively charged. Chloride ion, chloride ion. So all the negatively charged ions hang around the positively charged sodium and vice versa, and that gives this crystal a cubic structure. If you look at olivine, the arrangement of the atoms are different. This should give this crystal kind of a long shape. So if you look at halite, that's what halite looks like. So here is the cube right there, there, and there. You can see it's nice and cubic. Why? Because that's how the atoms are arranged. Then look at the olivine. As we predicted, it doesn't look like a cube. It's kind of tall compared to its width. So that's what it means to say the structure or the arrangement of the atoms in a crystal decides the properties of minerals. Let's look at a very interesting example how the structure or the arrangements of the atoms decides the properties of a mineral. Take diamond, the hardest mineral, with a hardness of 10, and take graphite, the material that forms the marking point of a pencil. Although it is called lead, it is not lead, it's just carbon. So diamond is made of carbon, graphite is made of carbon. Why is the diamond of hardness 10 the hardest mineral, and the graphite is one of the softest minerals between 1 and 2? It's so soft, that's why you use it for pencils. Look at the structure of these. You can see that graphite structure looks like this. So there are sheets of atoms, carbon atoms. So both are carbon atoms. These tiny spheres at the center of all at the junction of all these lines are carbon atoms. So graphite and diamond are both made of carbon. So the composition is the same. Why are they so different in their hardness? The arrangements. So the carbon atoms in graphite make sheets. So if you rub these sheets, the sheets will break apart easily because the bond between sheets is very long. So this part will break away. That's what happens. And if you look at diamond, the bonds are equal in length, therefore equal in strength. So you cannot break it. They are so close to each other and very same length in all directions. So that makes the hardness to go up to 10. So this is a clear example of how the structure or the arrangement of atoms in a crystal decides the property, in this case hardness, of a mineral. That brings our discussion on minerals to an end. I would like you to notice that we looked at so many different minerals and we learned lots of names and all that. There's a lot to remember in terms of minerals and understand, but I would like you to understand only major parts about that discussion. To understand what you need to remember, I would like you to look at the review questions on minerals. Okay, so you are expected to memorize about 15 minerals, their names, their class, and some of their properties. So, and also their classification, which group they do belong to. So I'm going to upload a page that shows the classification and Mohs scale as a single page, so you can download, print it, and put it in your notes. Take that and also look at your review questions and tell yourselves, these are the things that I need to remember. I don't think there's a question on lepidolite. Lepidolite is a very interesting purple colored mica now we use to extract lithium from to make lithium ion batteries for all our electric cars and trucks and all that. Make sure that you read the review questions and understand the material that is in there. Okay? Alright, have a great day. If you have any questions, email me.